Good day, students. In this clip, we're going to be going over part 2 of the modeling and optimization problems. And in this case, we're going to be dealing with a cylindrical can situation. All right, so let's go over the steps again. I went over these in part 1, but we're still going to use the same procedure to do these problems. So step 1 is you want to model the situation using a diagram or a graph, and then you want to create your optimization and primary function, optimization of primary functions and your constraint functions. Part 2, you're going to substitute an isolated variable from your constraint or secondary function into your optimization of primary function. Part 3, you find the potential extremas by looking for critical points and endpoints. If you are dealing with a closed situation, that's when endpoints are applicable, or else you just look for your critical points. And in part 4, you're going to classify your extrema, verify if it's a max or min, either by using the first derivative or the second derivative test. But you can also evaluate the endpoints to determine if they are actually the extremas, okay? And in part 5, you just state the meaning of your results. All right, let's take a look at part 2, or number 2. It says you're to create an enclosed cylindrical tank to hold 64 cubic feet of petroleum distillate with steel sheets. What are the dimensions of the cylinder that will use the least amount of steel sheets? All right, so for part 1, we are going to create a mathematical model of the situation. Okay, so we're going to model the situation for part 1. So first thing we're going to do is we're going to sketch the graph. We're just going to draw a cylindrical tank. All right, so there goes my cylindrical tank. Now let me basically label the measures here that are relevant. So for your cylinder, it's good to know if you want to calculate the volume and the surface area, you want to know the height of your cylindrical tank. We're going to call that H. So let's call the height H. And then the radius is going to be R. Okay, so the radius of our cylindrical tank, let's call that R. All right, so the height is H and the radius is R. Okay, let's start off with our optimization function. Optimization or primary function. Optimization or primary function. So what are we optimizing in this problem? We're asked to determine the dimensions that we use the least amount of steel sheets. Okay, so what are the steel sheets used for? Is it going to be the enclosure, the exterior, or the volume? If we're looking at the steel sheets, we're basically looking at the surface area of the tank. Okay, so we're optimizing the surface area because that's what we're using our steel sheets to do, right? To build the exterior, the surface area. And since it is enclosed, we're going to be looking at the top, the bottom, and also the sides. All right. Okay, so now let's write down the volume of the surface area of this cylinder right here. So surface area, let's call that S. Surface area is going to be the area of the top and the bottom. The top and the bottom are two circles, so that's going to be 2 times pi r squared. Remember, the area of a circle is pi r squared. All right, how about the lateral area, the area of the. Now, if you cut this cylindrical tank by the side and laid out the lateral area, what is it going to look like? What you're going to have is a rectangle. So if you take a look at this applet right here, this is a cylinder on the side. So earlier we said that the top and the bottom are going to be 2 pi r squared. That's these two sides. How about the area of the lateral area? Well, basically, if you cut it and lay it out, it's going to become a rectangle. Okay, let me show that to you real quick. So if I lay it out like this, what do you see happening? You have a rectangle. That's the lateral area. So 2 pi r h will be the area of the rectangle. H is basically the height, and this 2 pi r is the same as the circumference of the circle. So that's why it's 2 pi r h. Okay, see how that plays out? So this length right here is the same thing as the circumference of the circle. Okay, so the area of this rectangle is length times width. The length is 2 pi r, and the height is h. Okay. All right, so now let's go ahead and write down this is the area of the top and the bottom plus the lateral area is 2 pi r is the length times h, which is the width of the rectangle, the resulting rectangle, if you disassemble this cylinder right here. All right, so that was your optimization function. And if you notice, we have two variables here. Hopefully our constraint can help get rid of that problem for us. Okay. All right, so now let's take a look at the constraint function. So optimization, we were focusing on the surface area, and then for the constraint function, let me change the color of that. Let's make it blue. So constraint function, constraint. What is the constraint here? What are we constrained by? What is the limit? How much liquid are we supposed to hold? We're supposed to hold 64 cubic feet. So the constraint is the volume, okay? So we're constrained by the volume, which has to be equal to 64 cubic feet. Okay, so there goes our constraint right there. All right, now let's write down the equation. What's the equation of the volume of a cylinder? We know what that is, right? The volume of a cylinder is given by the area of the base, which is pi r squared, times the perpendicular height, which is h. Okay? All right, this has to be equal to 64. So we have pi r squared h equals 64. Now, if I wanted to isolate a variable here for substitution in part 2, which is the easiest variable to isolate? If I wanted to isolate r, I'll have a radical, and then denominator doesn't look too pretty, but how about we isolate h? Okay, so to isolate h, we just basically divide both sides by pi r squared, pi r squared, and then we'll have, what do we have? We'll have h, change color here, sorry about this. We have h equals 64 over pi r squared. Okay, so this is a constraint function with one variable isolated. All right, so now let's take a look at part 2. Part 2, we're going to substitute and state the domain. Okay, substitute and domain. All right, so we noticed that in part 1 we had this h in the constraint nicely isolated, so we can make a nice substitution here. So let's go ahead and do the substitution. The surface area as a function of r is now going to be 2 pi r squared plus 2 pi r. Now instead of h, we're going to substitute the value of h that's written in terms of r here, which is 64 over pi r squared. Okay, 64 over pi r squared. So now we have this one variable that's functioning in terms of one variable that is easy to differentiate. Okay, all right, so let's go ahead and simplify this resulting function. We're going to have s of r is equal to 2 pi r squared plus going to simplify to 128 over r. So basically you have the r cancel, this r goes here once, so this r goes here once, and then this pi cancels out with this pi, and then 2 times 64 is 128 over r. Okay, so this is our surface area function in terms of r. Okay, next thing we have to do is we need to state the domain of this function. So let's write it down, domain. So this is the function and then domain. Now, first thing you can notice off the bat is that there is a r in the denominator here, which means that r cannot be 0. Okay? Now, can r be negative? Let's take a look at the situation. We're dealing with the measures of a figure, namely the radius of a cylinder. Can a radius have a negative measure or negative value? The answer is absolutely not. So we know that r cannot be negative, r can only be positive. Okay? So we know for one thing that r has to be bigger than 0. Now how big can r be, or how small can can r be as long as it's bigger than 0? Now, if we get infinitely close to 0, what happens is that this term right here gets really, really small, and this term dominates. As r approaches 0 from the right, this term approaches infinity, and this term approaches 0. So this term dominates. It gets infinitely large. Okay? Now, if r approaches infinity, what happens? If r approaches infinity, this term goes to 0, and this term dominates. It gets infinitely large. All right? So what does that tell us? It tells us that there are no constraints on r as long as it's bigger than 0. So our domain is r is greater than 0, or you can write it as 0 to infinity. Now, what does this tell us? It tells us that r is in an open interval. It's not a closed interval. Hence, the endpoints are not going to be considered when looking for extremas because there aren't any endpoints, all right? Okay, so there goes the function and the domain, part 3. What we're going to do now is we're going to find the extremas, okay? Extremas. The potential extremas, because we do not know yet until we do the classification. All right. All right, so for potential extremas, what we're going to be looking for here are the critical points and endpoints, okay? But since the endpoints are not valid in this problem, it's an open interval, all we're just going to look for are the critical points. Okay, so let's go ahead and do that. What we're going to do is find critical points. So find the critical points. Now, what are the critical points? The critical points are where f prime. Well, in this problem, we're dealing with s, right? So let's call it s. So in this case, critical points are where s prime is equal to 0 or s prime does not exist. Okay? So those are the values of r that we're going to be looking for in this part of the problem. Okay, so let's rewrite the function under consideration. We have, let's see, s of r is equal to 2 pi r squared plus 128 over r. Now, let's differentiate this function. But before we differentiate it, we can rewrite this portion so it's easier to differentiate. I don't want to use the quotient rule if I don't have to. So this is going to can be written as 2 pi r squared plus what? Plus 128 r raised to the negative 1 using the reciprocal property of exponents, okay? Now it's easy to differentiate simply by using the power rule. So s prime of r. So for the first portion here, 2 pi r squared, we take the derivative, that will be 4 pi r. And then the derivative of this is in the power rule. This minus times this positive will become minus 1 times 128 r. And then we decrease this degree by 1, so minus 2. Okay? So we can rewrite this as 4 pi r minus 128 over r squared. Now let's combine these two. I like to write my derivative as a numerator and denominator so we can know exactly where it's equal to 0, the numerator, and where it does not exist, which is basically the denominator component. All right. So put this over 1, and let's unite them. We need to find the LCD. Times this by r squared top and bottom, and our derivative as prime of r in combined form is going to be 4 pi r to the third minus 128. This entire thing divided by r squared. Okay. All right. Now, remember when we're looking for critical points, we need to break the problem up into two parts, where the derivative is equal to 0 and when it's non-existent. Okay, so we're going to find where s prime of r is equal to 0, and then where s prime of r does not exist. All right, so let's do the first one. So when you're looking for when the derivative is 0, you can simply just extract the numerator and set to 0, and that will suffice. Because if you set the whole thing to 0 and you cross multiply, what happens to the denominator? The denominator gets cancelled out because r squared times 0 is r. So let's forget that step and just set the numerator to 0, okay? Now if I move 128 to the other side, I have 4 pi r cubed is equal to 128. Divide both sides by 4 pi, and we'll have r to the third is 128 over 4 pi. And if you divide top and bottom by 4, this will give you 32 over pi. And then when you take the cube root, you're going to end up with r is equal to the cube root of 32 over pi. So that's the only critical point that we have. I'm sorry, the only point where the derivative is 0. Critical points that involves the non-existence of the derivative, we have to set the denominator to 0 because that's what makes the derivative undefined. And we know that wherever the derivative is undefined, we have a critical point there. So what we're going to do is set r squared equal to 0. That's the denominator. Take the square root of both sides. We'll have r is equal to 0. Okay? So should we consider this in our problem? The answer is no. Do you know why we are not going to consider r equals 0? Because it's outside our domain. Remember, we said that r cannot be 0 because it's going to cause our area to be undefined right here. So in our domain restrictions, r has to be 0 or greater. And we have a critical point where r is equal to 0. Since it's outside the domain, we're going to drop this off, okay? So this one violates our domain constraint, so we're going to drop it off. All right, so this is the only critical point or potential extrema that we have, all right? So what we're doing in this problem is we're looking for the minimum. We're trying to find the least amount of material. So let's classify this. We're going to do a classification. Now, if we can show that this is a minimum at this point, then we have accomplished our goal. All right, so let's classify. Now, we're going to use the second derivative test. If a point is a minimum, then the concavity has to be upwards. Okay, and if the function is concave up, that tells us that the second derivative, s double prime, has to be positive. So if the second derivative is positive, here at this r value, then we're confident that this is in fact the minimum. Okay, and then that's the value that minimizes the area. So let's do the second derivative test. Basically, we're looking for f double prime has to be greater than 0. Okay, that implies upward concavity. All right, let's do that. So we have the derivative function s prime of r. I don't remember what it is, so let's scroll a bit. Where are you? Okay, let me use this form right here. So 4 pi r squared. So it's going to be 4 pi r squared minus 128 r to the negative 2 actually just 4 pi r, so 4 pi r 4 pi r minus 128 r to the negative 2. So we're going to differentiate that again. Scratch this out. All right, so let's differentiate that again. So the derivative is going to be the second derivative, s s double prime, s double prime of r is going to be 4 pi, because the derivative of r is just 1, minus, factor this out, 128. The derivative of r to the negative 2 is going to be negative 2 r to the negative 3. Okay, and then when we simplify that, we're going to have s double prime of r equals 4 pi minus times minus is a plus 128 divided by r to the third. Okay, so just by looking at this, what can we conclude? Just by looking at this function, you notice that for our domain constraint, r is always bigger than 0. Okay, so since r is always bigger than 0, if we plug a positive number in this expression, what's going to happen? S double prime is going to be positive. Okay, so since Since r is greater than 0, s double prime of r is always positive. Always, it's always going to be positive. We don't even actually have to check it because this expression shows us that is whatever value of r we plug in, as long as it's positive, the resulting uh, answer will be positive. So s double prime is always positive, hence s of r is concave up. It's concave up at r equals the cube root of 32 divided by, let's see, what did we get? 32 divided by pi. So it's concave up there, okay? And a minimum exists here. Okay, so by second derivative test, if the second derivative is, if the second derivative is positive and you have a critical point there, that critical point is going to be a minimum. All right, so that's the kind of situation we have. All right, so that's basically the value that we're looking for here. Now we're going to shift to part 4, where we're going to state our conclusion. All right, so let's state our conclusion. Part 4, conclusion. All right, so for this part, well, we know what h r is. We're asked to state the dimensions of the steel of the cylindrical tank. All right, so we know that r is equal to the cube root of 32 over pi. And what is the height going to be, though? What is h going to be? We know that we found out earlier in the problem that h was equal to, h was 64 over r squared. Okay, h was 64 over r squared over pi r squared. That's what we had earlier. Remember when we were looking for the constraint function in terms of h, we have this. So now let's plug in the value of r into this function right here. So to get what h is, all right? So h is equal to 64 divided by pi times the cube root of 32 over pi square. All right, so let's go ahead and simplify this. To make it easy to simplify, how about we express everything in terms of cubes? Now, cube roots to be specific. Now you notice there's a 32 here, so I can factor out a 2 out of this top numerator so that it's consistent with this 32 right here. So I want to write this as follows. So factor out a 2. And then 2 times. Now let's express, if I take out 2 from here, I'll be left with 32, but I can write 32 as 32 to the third power raised to the 1/3. Okay, 32 to the third power raised to 1/3 is just 32, same thing. And then on the denominator, pi can also be written as pi to the third raised to the 1/3, right? Because they just cancel out. And in this business right here, I can write it as 32 over pi raised to the 2/3. So the reason why I did this is I want all the denominators of all the fractions to be identical. Basically, I want them to all be 3's, okay? So if they're all 3's, I can factor this out, and I can write it as 2 times 2 times 32, right, it's 32 to the third power, 32 to the third power over, let's see, pi to the third times 32 square over pi square, the entire thing raised to the 1/3. Okay, what did I just do here? what did I just do? I just took out the 1/3 power from all three terms, okay? And then this square right here, I distributed to the 32 and also to the pi. Okay, so what happens with this setup? What happens is that, see this pi square cancels with that, and then this 32 square just takes out one of these powers right here, and what are we left with? We're left with 32 times 32 over pi raised to the 1/3, right? 32 over pi raised to the 1/3, which is equal to 2 times the cube root of 32 over pi. Okay? Now, does this look familiar, though? Does that look familiar? It should. This piece right here is the same as r. Okay? So it's basically equal to 2r. So that's basically what it is. R is equal to 2r. All right, so dimensions of our the dimensions of our cylindrical tank. All right, so let's write it down. The dimensions of our 64 cubic feet cylindrical tank that holds the least, that uses the least material, has a radius of the cube root of root 32 over pi and a height of double that, 2 times the cube root of 32 over pi. Okay? And if you want to find the approximation of this, you can plug this into your calculator. And the approximate value, you can write it like that, or r is approximately 2.1677, I'm going to put the units there, feet. And h is double that. If you double that, you get 4.3354 feet. Okay, so there goes your answer. This is the exact value, and this is just an approximation of the results. Okay, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking subscribe here. And please post a comment to let me know what you think about this clip. And do give me a thumbs up if you liked it. I appreciate it. More clips can be found on mathgotserved.com/calculus. Thanks again for watching and have a wonderful